Hello everyone, my name is Mojgan Purkeshavaz and I'm going to present our recent work at CVPR titled CaDeT, a causal disentanglement approach for robust trajectory prediction in autonomous driving. This work was done in Noah's Ark lab and supervised by Amir Rasuli. For safe motion planning in real-world autonomous vehicles require behavior prediction models that are reliable and robust to distribution shifts. However, recent studies suggest that existing learning-based prediction models are susceptible to small perturbations that are not present in training data, largely due to overfitting to spurious correlations while learning. Consequently, spurious correlations create a backdoor path between non-causal features and predictions, leading to a lack of generalizability in prediction models. To overcome this issue, simply utilizing large-scale models or data cannot effectively and efficiently achieve generalizability. In fact, it's rooted in the statistical learning methods which prioritize correlation over robustness. Motivated by this insight, in this work we focus on the robustness and generalizability of trajectory prediction models against potential distribution shift in the inference phase. Here we provide an overview of the proposed approach. In detail, beginning with the scene encoding step, we encode the driving scene as a dynamic heterogeneous information network called DIHIN, with the node types, lane and agent, and the edge types preserving various relations in the lane graph and the connections between the lane and agents. Through the constructed DIHIN, we seek to separate causal and spurious features for each node. To do so, in the causal disentanglement step, a disentangled attention block is used to calculate the scores among the nodes in the dynamic neighborhood of each node in order to obtain disentanglement mask. In the uncertainty-driven intervention phase, having obtained spurious features, we estimate the potential uncertain statistic shifts to approximate intervened distributions. For this end, we use the variance of the mini-batch statistics in a non-parametric manner. And finally, we optimize the model by minimizing both prediction loss, which is based on only causal representation, and invariance loss, which measures the variance of the model's prediction under intervened distributions. We control the impact of the invariance loss using the lambda parameter. Our model achieves a state-of-the-art performance on most metrics on the well-known Argoverse 2 dataset. Additionally, compared to significantly more complex ensemble methods, our model has comparable performance. We also provide qualitative examples or real-life scenarios showcasing the reasonable causality score produced by our method. We further evaluate our model's generalization and robustness against potential distribution shifts through 3 experiments. In the first experiment, we apply adversarial perturbation to the observed dynamics of the agent in the input scene. We compare our model against forecast MAE, which is the state-of-the-art model trained using a self-supervised learning technique for robust and generalizable contextual feature learning. The findings suggest that the proposed model is significantly more robust as the performance degradation is drastically lower and the degradation level and robustness also remain similar across different training sizes. In the next experiment, we split the train and validation data of the Argoverse 2 into 2 non-overlapping sets based on the 6 cities that the data was collected from. Then we trained the model on the data from the first set of cities and evaluated on the unseen ones. The results indicate that our method significantly outperforms forecast MAE in all metrics. Lastly, we evaluate our model from the causality perspective. To this end, we conduct an experiment using the newly released causal annotation on the validation subset of the Waymo dataset. We use non-causal subset where all the non-causal agents from the scenes are removed. As presented in the table, the proposed model, besides being comparable or even better on the test set, demonstrates a higher level of robustness even when trained on the 50% of the data. Finally, we conduct an ablative study to evaluate the design choices in our proposed framework. To this end, we create several variations of our model and evaluate them on Argoverse 2 validation set. From the table, we can conclude 3 points. First, the representation disentanglement block is the prerequisite for robust prediction. Second, temporal patterns have a higher potential to create a spurious correlation. And lastly, uncertainty sampling is necessary to maintain the realism of the intervention. Furthermore, we determine the sensitivity of the lambda parameter. As shown in the figure, there is a drop in the performance where lambda parameter is either too small or too large. If lambda is set too small, the model does not suppress the spurious features effectively. And if it's set too large, the model fails to learn the causal features. In summary, in this work, we propose a causal disentanglement approach to disentangle causal and spurious features for more robust learning. Our method benefits from a novel intervention mechanism that simulates the potential distribution shift by incorporating uncertainty modeling in the latent space. To facilitate learning, we propose a novel training objective that leverages causal factors to enhance model resilience against potential distribution shifts. We conducted extensive experiments on 2 large-scale autonomous driving datasets and showed that besides achieving state-of-the-art performance, our method can significantly improve prediction robustness to various distribution shifts in the driving scene. Thanks for watching this video, and for more details, please check our paper and feel free to ask any questions.